Okay, so this is a continuation of the previous video lecture on the definition of the limit of a function. Okay, so from the previous video lecture, we have presented by the definition of the limit of a function in terms of the definition of the epsilon and delta pair. Okay, so let's try to illustrate that further using the illustration here presented on your screen. So from the definition of the limit of a function, we try to recall that we are presented by this expression: limit of f of x is equal to L as x approaches a, means that for every positive epsilon there exists a delta such that this if expression, then this f of x minus L expression for less than epsilon. To understand further this one, let's try to relate that with the illustration here on your screen. Okay, so again, as the value of x approaches a particular value of a function, in this case our f of x is defined by this red line. Okay, so this red line here is our graph of our f of x. Now, defining a particular value delta at a particular value a, the approach of a means that you define the open interval a plus delta and a minus delta. This corresponds to what we call a delta neighborhood for around the vicinity of a, and that would correspond to the interval which limits the location where we could find the value L. Now L defined on a, if that exists, we could find the value of L on the y-axis, and within the open interval, the distance from L towards a point above A on your y-axis, that distance is defined by epsilon. That means this point here is actually your L plus epsilon, and this point here is your L minus epsilon. Within this range of L minus epsilon and L plus epsilon, we define this interval as the neighborhood around L. What this illustration indicates is that whenever we define a neighborhood around L, we correspondingly define our delta neighborhood around A. So whenever we approach the value of A within that interval, we actually approach the value of f of x to L. Okay, so that is what is meant by our definition of our limit of a function. Now, to concretize the concept, let's try to apply the concept using a few examples. So for example, we have number 2. Prove using the definition that the limit of the expression 3x minus 5 as x approaches 4 is equal to 7. So using the definition, that means whenever we have a value a, wherein the value of a is the one that is approached by x, if that produces that points a value on our y-axis, and that particular value on the y-axis is our L. If we substitute a on our function, then that would point to the value L on the y-axis. So that means if we substitute the value of 4 on our x approaches 4, then that gives us 3 times 4, that is 12, minus 5, that gives us 7, and therefore the limit of 3x minus 5 as x approaches 4 is equal to 7. Now let's have another one. We have, to further illustrate this idea, again using the delta epsilon relationship, if a here represents or if this function here, the blue one, is your expression 3x minus 5, and a here is your 4, then defining your delta within this given neighborhood by substitution of a in the given function, this should point to the value L of L on the y-axis, the value of f of x at that particular point corresponding to the location of A on the x-axis. So we could find, obviously based on the definition, that we could find the value of L within the vicinity of L plus epsilon and L minus epsilon. And this epsilon neighborhood is actually given within this vicinity. Okay, so by direct substitution, since the limit of this expression is defined at 4, we know that the limit of the function at 4 is defined since the expression does not result into a fraction that is undefined at this location. Therefore, the limit exists at this location. If the limit exists, we know that the limit exists, we could directly substitute the value of x in the form of the function and determine the limit of the function using using basic algebra. So that means we could find 3 times 4 equals 12 minus 5 gives us 7, and 7 would be the limit of this function. Now similarly, for example number 3, show that the limit of 1 over x as x approaches 0 does not exist. Obviously, if we do a direct substitution of the value of x equals 0 to the expression 1 over x, that would result into a function that is undefined. 1 over x is undefined. Now, using the definition of delta and epsilon, we know that the limit of 1 over x does not exist, because if we define, for example, the vicinity of our epsilon within an interval such as between 0 and 1, we know that the delta neighborhood would be within this vicinity. And based on this illustration here, if you try to plot the values of 1 over x as for values above or below x, we know that the resulting values for values of x wherein x are positive values corresponds to this graph. If we substitute values of x wherein x are negative, the values of x would result to this graph. Now, since we are not allowed to substitute x is equal to 0, then the values of the graph would have space on the value of x corresponding to 0. That means the value of the value of the graph approaches the y-axis at 0, but never reaching the actual value 0 for both approach in the positive values and the negative values. Now, if we define a neighborhood within this vicinity, we could find that we would take note that the neighborhood would be defined within this interval, and there are values outside the interval of our epsilon. Then that means it would not conform with the definition of our definition of a function, that whenever you define an epsilon neighborhood, there exists a delta neighborhood such that we could find x within the delta neighborhood, so that we could find L within the epsilon neighborhood. As we can see from the graph of the function, this is our this is our epsilon neighborhood, and this is correspondingly this is our epsilon neighborhood. Let me repeat that. If this is our epsilon neighborhood and this is our delta neighborhood, there are values within the epsilon neighborhood where we could find L outside the epsilon neighborhood. Since this is our epsilon neighborhood and L is outside of that, then that means the limit of 1 over x as x approaches 0 does not exist. Okay, so let's have example number 4. If f of x is equal to the absolute value of x over x, show that the limit of f of x as x approaches 0 does not exist. Okay, so again, we define the absolute value, we define the form of the function. We take note if we try to graph the values of this function, f of x is equal to the absolute value of x is equal over x, then we could find that the graph of the function would be this one. Since x is in the form of an absolute value, if we assign positive values for x, for example, x is equal to any positive value, then we could find that the value of f of x is any line that would fall on a line that is horizontal. So, for example, if we let x equal to 1, therefore we have y is equal to 1, and all assigned values for x would fall along this line. Now, suppose x is equal to -1, then that means that any value of assigned integrating function would fall within this vicinity. Now, if we define a value epsilon, so that we could, for example, have this L plus epsilon and y L minus epsilon as our epsilon neighborhood, then our delta neighborhood obviously would be within this vicinity. Then that means there are values outside within the epsilon neighborhood. That means that the value of L, we could find any value of L outside within the vicinity. Then that means it is not in conformity with the definition. With this definition, because the value of L, we could find a value of L outside epsilon, the epsilon neighborhood, then that means the value of L does not exist. Okay, so at this point, let us now define some techniques in finding the limits of a function. Okay, so let's have the following. The first one is the limit of a constant. So, for example, 2 or 4 or any other number. Square root of 2, 1/3, 1/4, -1. The limit of a constant as x approaches any value is equal to the constant. So, for example, the limit of 3 as x approaches 0 is equal to 3. The limit of -1/3 as x approaches 4 is -1/3. Number 2, the limit of x as x approaches a is equal to a. That means we only need to substitute the value of a, replacing the value for the value of x. Okay, here let's have the second theorem. The limit of f of x as x approaches a, and given the limit of f of x and the limit of g of x, if both of these two limits exist, then the limit of the sum of the function is equal to the sum of the limits of the two functions. The limit of the difference between the two functions is equal to the difference of the limit of the two functions. Also, the limit of the product of the two functions is equal to the product of the limits of the two functions. Number 3, the limit of the quotient of the two functions is equal to the quotient of the limits of the two functions, provided that the limit of g of x is not equal to 0. If you have the form of the function wherein you have f of x multiplied by a constant, that is the same as saying c, the limit of f of x. Now, if you have m, the following constants m, b, and a, and these are real numbers, then the limit of the form m times x plus b is equal to m times a plus b, wherein we have substituted the value of a for x as x approaches a. Now, number 4, if n is a positive integer, then the form of the limit of the function for x raised to n as x approaches a is equal to a raised to n. Number 2, if the limit of f of x raised to n as x approaches a, that is the same as saying as the limit of f of x as x approaches a raised to n, provided that, of course, the limit of f of x exists. Now, number 5, if f is a polynomial function and a is a real number, then the limit of f of x as x approaches a is simply f of a. If q is a rational function and a is in the domain of q, then the limit of q of x as x approaches a is q of a. Now, if you have the form of the function that has radicals, provided that if that a is positive and n is a positive integer, if a is less than or equal to 0 and n is an odd positive integer, then the limit of the nth root of x as x approaches a is the nth root of a. Now let's try to answer the following examples. Now you have the limit of 3x plus 4 over 5x plus 7. Now take note that since you have a quotient for the form of the function, what we took note of from the previous theorems is that if you have a quotient, it should be provided that the limit of g of x is not equal to 0. That means 5x plus 7 should not be equal to 0, or the limit of 5x plus 7 is not equal to 0. Now, what this example means, that since this is in quotient form, that means we are going to apply number 3 here. So number 3 suggests that the limit of the quotient of the two functions is equal to the quotient of the limit of the two functions. So that means simply we try to get the limit of 3x plus 4, we try to get the limit of 5x plus 7, then divide the two limits, and what would that yield is that would be equal to the limit of the whole function. So by substitution, the limit of 3x plus 4 is simply we substitute x 2 for x. That means you have 2 times 3 is 6 plus 4. That would be 10. While 5 times 2 is 10 plus 7, 17. So you have 10 over 17. The limit of this function as x approaches 2 is 10 over 17. Okay, so the limit of x cubed as x approaches a is a cube. Now for the rest of the examples, example 7, example 8, example 9, I will 10, 11, and up to 11, I have to ask you that this would serve as seed work or part of the problem set. Example 7, example 8, example 9, and example 10. Example 10 and example 11. Try to apply the theorems that were presented earlier.